Let's jump right into this explainer. Today, we're taking a dynamic look at the actual foundation of modern civilization. Look, there's this really common myth out there that metallurgy is, some outdated field, kind of stuck in the Industrial Revolution with anvils and hammers. But the reality? No way. We are literally discovering entirely new states of metals right now. We're talking about the science of shaping the entire physical world. Everything from the massive steel beams holding up skyscrapers to the ultralight titanium alloys pushing boundaries in space exploration. Okay, let's dive right into our roadmap for today. First, we'll cover what modern metallurgy actually is. Then, we'll go inside the four-year degree. After that, the real stuff: careers, salaries, and daily life. Then we'll look at the future: AI and sustainability. And finally, we'll figure out if this path is actually for you. Let's get started. All right, section 1. What is modern metallurgy? I like to call this the hidden engine of the modern world. Have you ever stopped to ask yourself what actually holds up the modern world? I mean, literally, every single object around you relies on materials engineering. That smartphone you're probably holding, it relies on incredibly complex lithium-ion cathode materials. The bridges we drive over every day, they need high-strength steel. Those jets flying overhead, they absolutely depend on advanced titanium. None of this, and I mean none of it, exists without a materials engineer sitting down and figuring out exactly what to use and how to process it. So the absolutely crucial thing to understand here is that metallurgists don't just use materials, they literally design them. And it all revolves around this idea called the Processing Structure Properties Performance Framework, or PSP. Basically, you're deliberately designing a material's internal microscopic atomic architecture to get a very specific real-world outcome. For example, by changing how a metal is processed, like if you rapidly cool or quench hot steel, you completely alter its internal crystal structure. And doing that drastically changes its strength and how it performs. It's like a giant atomic puzzle. Moving on to section 2, inside the four-year degree. Let's call this the academic crucible. So how does this degree actually play out? Well, the progression is incredibly fast-paced and honestly fascinating. In year 1, you're building a massive foundation in math, physics, and chemistry. Then year 2 is where the magic really starts happening. You dive straight into core specializations like phase transformations and thermodynamics. By year 3, you're doing an advanced deep dive into the massive industrial processes like making steel and figuring out exactly why materials fail. And finally, year 4 is the whole shebang: pure specialization and a major B-Tech project. And a lot of times, these projects are co-supervised by absolute industry giants like Tata Steel or ISRO. Now, you might be wondering, why do those foundational sciences from year 1 matter so much? Well, it's because chemistry and physics are the literal language of material science. Your physical chemistry knowledge, especially thermodynamics, is hyper-relevant here. It's the absolute backbone for understanding why certain phases of metal are stable at specific temperatures. It lets you predict and control microstructures. Those hidden geometric patterns that actually give metals their strength. And hey, you aren't just going to be burying your head in textbooks. You are building a highly marketable technical toolkit. You'll learn to use incredibly sophisticated and, let's face it, very expensive instruments like scanning and transmission electron microscopes. And trust me, proficiency with these tools is genuinely rare in the job market. Combine that hardware experience with computational skills like Python, machine learning, and thermodynamic modeling like CalPad, you become absolutely invaluable to modern industry. All right, section 3, careers, salaries, and daily life. Let's get into the pragmatic reality. We definitely need to talk numbers here. Let's be radically honest. There is a visible salary gap at the entry level between core metallurgy roles and the IT or computer science sector. Core roles might start between 8 to 14 lakhs per annum at top institutes, while IT roles can push way higher. But here is the trade-off. Core metallurgy offers immense stability. There is way less commodity competition, plus you're looking at a super solid long-term career trajectory where senior experts command massive premiums later on. And just look at where you could be working. These are high-purpose career paths. You've got the massive steel giants like Tata Steel and JSW. You have huge public sector options like SAIL, but maybe the coolest part? Defense and space giants like DRDO and ISRO specifically hire metallurgy grads over computer science engineers. Why? Because they desperately need experts to develop critical aerospace materials and rocket casings. If you want to have a hand in putting humanity in space, this is exactly how you get there. Oh, and don't forget the completely exploding sector of EV battery gigafactories.
But what does the day-to-day actually look like? Well, if you're a process metallurgist at a plant, it is fast-paced and it's physically demanding. Your morning might kick off with shift handovers and walking the really loud, scorching hot shop floor to monitor 1,500-degree blast furnaces. Then, your afternoon could be pure detective work, running a failure investigation to figure out why a specific batch of steel cracked. And the evening? That's about pushing improvement projects to optimize yield. It's incredibly hands-on, vital work.
That brings us to Section 4, the future, AI and sustainability, and how we're supercharging the field. To really grasp the demand in this field, just look at this number. India's national steel policy has a target of producing 300 million tons by 2030. To put that into perspective, that is a massive doubling of our current capacity. We're talking enough steel to build hundreds of entire cities. This proves there is a massive structural demand for thousands of new metallurgical engineers. Guys, this industry isn't shrinking, it is scaling up big time. And the technology is just evolving so rapidly. We're seeing a total revolution in EV battery materials right now with solid-state electrolytes. We've got high-entropy alloys that mix 5 or more elements together for extreme environments. There's metal 3D printing for aerospace. And we are aggressively moving towards green steel, which means replacing coal with hydrogen to virtually eliminate carbon emissions. This brilliantly illustrates how metallurgy is actually right at the bleeding edge of global sustainable innovation. Now, this evolution, it accelerates even faster when you bring artificial intelligence into the mix. AI is literally compressing alloy design from years down to just months. We have machine learning models predicting phase stability without needing to run super expensive physical experiments. Computer vision is automating all that tedious microscope analysis in seconds. And we're using digital twins, which are basically virtual replicas of the factory, to optimize blast furnaces in real time. It's a real game changer. But here is the absolutely critical takeaway. AI cannot replace physical metallurgy intuition. Sure, AI is fantastic at raising the floor for routine tasks, but when a completely novel failure mode happens on the shop floor, something that AI has never ever seen in its training data, guess what? It takes a human engineer. It takes someone with deep physical intuition and a real understanding of atomic structures to diagnose and solve that problem. Finally, Section 5. Is this for you? The radically honest decision framework. Let's be super transparent here to help you decide. You are going to thrive in this field if you are genuinely fascinated by materials, if you are strong in both chemistry and physics, and if the whole idea of working in heavy industry or national defense gets you excited. On the flip side, you might struggle if your ultimate goal is purely software and IT, if you absolutely hated thermodynamics, or if working exclusively in a major, shiny metro city is a deal breaker for you. I want you to do a quick self-assessment right now. When you see a Boeing 787 airplane, do you naturally wonder why they used carbon fiber for the fuselage instead of, say, aluminum? If your brain naturally gravitates toward the what and the how of the physical world around you, you absolutely have the exact kind of curiosity required for this branch. So if you're leaning towards yes, here are your actionable next steps. Go watch some free NPTL lectures online, particularly the ones by Professor R.N. Ghosh. They're great. Read the first chapter of Callister's Materials Science textbook. Start learning Python right now. And definitely go explore the Free Materials Project database to see what computational materials science actually looks like in practice. The resources are all right there. Don't wait to start exploring this path today. Everything we build and everything we will ever invent relies entirely on the physical stuff it's made of. The world is made of materials. And the engineers who understand these materials best, they will literally shape the world that comes next. So the only question left to ask is, will you be one of them?